Yeah, thanks a lot. So I'm sharing my screen. Do you see everything? Everything is fine, I hope.
Yes.
Okay. So thanks a lot for giving me time to talk here. So yes, thank you, Susanna. Always great to see this simulation, and I'm very excited to see that. Yeah, I will introduce like the transition, let's say, towards the observation here, and of course, my main collaborator. I just want to say is of course Ben Freiter, that is also listening here, but also Caterina Cracento had me a lot also in these things that I will show here, and all the other that are below. Of course, Matisse Vega instrument groups in Nice, the Chara group as well, Miguel, Marcus, Claudia, Xavier, Ryan Norris et al., many others. So yeah, I will go a little bit fast on these things, but I want to insist, of course, just give you, because Susanna just already introduced that, but I want to give like some numbers now. So about red supergiant, what I'm going to talk about an HEV. So I'm going to talk about the two things to show you some observations. These stars are these stellar parameters that I show here. The HEV that more lower masses, more less luminous, but still big stuff. But the point I want to talk about is exactly what Susanna pointed out: is the very extreme mass loss, which is depends on stars, depends on what we know we are exploring, but it's actually an interplay between convection motion, acoustic wave, radiation pressure, or molecular lines and dust, maybe also magnetic fields, etc. And also this is extremely huge, like 7 to 10 order magnitude larger than what we have in the sun. And the idea to concentrate me on this talk is really the convective motions. The convective motion just already been said by Susanna. I just want to point out the big picture. If you have a look now in the main sequence star like the sun, what we are interested in actually in this, the photosphere where we see the flux coming from the star is actually coming from the very, very top layer. So we indicate this with these blue things. Where we're talking about red supergiants actually is the full convective pattern of the envelope of the star. So this is it's important to be taken into account. That's why we do the simulation that Susanne introduced here. To example, you have volumetric intensity for the HEV on the top, and you have a density pattern. I think it was on the bottom one. We do this cobalt, but the things I want to talk about now is the coupling of this with the Opt-in2D. So it's a radially transfer code that make post-processing, detailed post-processing of this simulation. So it takes like density, temperature, velocities, and just compute the observable interferometric, spectroscopy, photometry, astrometry. Everything is just to be used to compare to the observations. How do we do this? So just to make now we go to interferometry. If we have a typical observer is the closure phases on the right, we have like a uniform disk called Lindh-Ackland model. The closure phase signal is typical 0. Why we are, so I forgot to say why we're interested in that, because for instance, like the closure phase is what give us information about the morphology or the distribution of the spots, if you want to say, on the surface of the star we want to look at. When we go for such an image like the one on the left, we have like the 3D plot, if you wanted this intensity image, then the closure phases start to have signal. The closure phase, but also, of course, the visibility. So the contrast of the fringes are also important in this sense. And this makes an important step for the next one, which is how do we actually have a look to comparing what we see on the right, like an observation, the reconstructed images. I will show this in a few seconds later, and the synthetic image we produce from the models. First things, we want make a convolution, of course, of these images to have something more comparable to observations. And what we want to do is to put in evidence the presence of convective-related surface structures. So we do this in different ways and all together, actually. First things, we measure the intensity contrast using the law put by Tremble in 2013 for the first time. So we measure the contrast between the different structure in the synthetic images and in the observations. Second things, we account for the unknown orientation. So we don't know actually how this model is put with respect to the observation. So we rotate the synthetic star. We account, when possible, to the temporal variation. So you have here the intensity of a particular wavelength observed, so synthetic intensity moving as a function of time. We measure as well the photocenter position. So you can see that is not in the center already. And of course, the last things we try to take into account the wave independence. So this is high resolution, but basically when you look at the dip of a spectral line, you have a larger star. When we look, for instance, over molecular bands, when with respect when to look at to the continuum and the pseudo continuum of the star. So taking all this into account, we made several applications of this since 2009 until very recently. So you see that it's increasing the application of these models to try to explain the convection on these star with all with AGB, a supergiant, with all different kind of instruments. But I just want to concentrate to do things, the last things we did. One for an AGB and one for a supergiant star. So we start from the AGB one, so CL Lake, done with Merck X char. So this was correct me if I was wrong, but it was the first image done with with Merck X. This has been done in 2 nights with the mirror reconstruction images. So you have the UV plane on the top, and then you have two images at 2 different wavelengths. The number of points were, I mean, there were only 7 points in the wavelength bins. And you see that the photocenter is displaced. Why the photocenter is this, the barycentric position is this cross in the middle I put. So you see that this convective signal that we see is not actually at the center. Why I do show that? Because first, when we compare to the 3D simulation, we have something that converges also when we start from the synthetic images on the right. We convolve, we make the comparison as I said before, and we have the best fit that can explain the presence of convective related structure. But then the other thing is then we take this image here and we at the same size and we have a look to what we see in Gaia, for instance. Gaia sees the position of astrometric position of the Gaia G band. Now we have synthetic image on the left and we have the predicted photocenter position on the right. During the Gaia mission, this variability is very large, up to 5 to 10% of the radius of these AGB stars. So this is actually something intrinsic in the observation of this kind of star, and it's something that can actually be used to help to understand the physics of these stars. So you have a plot here on the left now of the luminosity as a function of the error bar on the parallax observed by Gaia in early DR3. And you see that the red stars are actually the photocenters that I just showed from the simulation. And on the right, sorry, the black points with error bars are the observations. And the funny thing is that they actually cover a substantial part of the Gaia early DR3 parallax error. But more even interesting is that when we look to a particular part, like at this point, for instance, it's actually CL Lake, for which we made observation with the Merck X, for which we determined the presence of convection. So thanks really to interferometry is really crucial here to determine the presence of, to confirm the presence of the stellar convection on the surface and help us to interpret in a really unique way the mass, radius, and convection properties of AGB and red supergiants, thanks to Gaia and interferometry. I go to my second example here for the last minutes I have. And so this is the Vix Sagittarius red supergiant we observed with the guaranteed time for Matisse. So in 2010, with Marcus, Florentin, Milura et al., we made an observation of this star in the H band with amber, in which we had a really wavelength dependencies of this. You can clearly see. So these are reconstructed image with the mirror for 3 nights. And we see really the star is becoming bigger. And this is, we found that this photosteric station was due to the presence of water in this star. And of course, we saw also the convective pattern thanks to the 3D simulation. We did the same now with Matisse, with 2 different wavelengths here. Now we on the top, you have the LM band. On the bottom, you have the end band. And then I make it run again. You see really the wavelength moving, and you see that the star is actually dependent on the wavelength you're looking at. So again, we could explain with the simulation the presence of different molecules, CO, SiO, water, OH, using 3-night observation and mirror reconstruction images.
2 minutes.
Just to make, 2 minutes, right? Yeah, but just to put on the scale, then we have just to give you the star, the LM band is actually really the very, very center part of the N band. So there is something more that is outside the simulation set that what has just been showed by Susanne. We are not using this kind of models, but we could have could actually explain the presence of a convective pattern. Like again, on the top, you have the AGB and supergiant, so we use different models. But I want also to show that we made a tentative dust qualitative comparison, because in this part, actually, the star, which is the blue dot on the left, is actually surrounded by something around, which is actually dust. And we try with a to explain this using different redundancy 3D approach and different dust components, but with not a very, just a qualitative approach. I have one last slide. I know that I finished my minutes. I just wanted to finish on this. How do we need to characterize the stellar convective simulations? We have really different bands here, and this is an AGB simulation. Hot, medium, and cold materials highlighted. And you see that the star appearance difference with respect to what are you probing in the different wavelength regions. Going from the higher infrared to the visible, you actually increase the contrast and you have more complex structure and you see better, let's say, the convection side. Let's say like this. When you go from the other side, from the visible to the higher infrared, you see more extended photosphere because of you have molecules contributing and decrease the contrast. So this is something that to be taken into account. But the last slide is this one. Is not only this, is what is also very mattering here is the monthly images, so the temporal, time-dependent observation on the left, and high resolving power to resolve the stratification, the photosphere, and the velocity field across the photosphere. So this is all needed to have a full picture of the dynamics of these stars and to connect this to the mass loss of this kind of objects. And I stop on this. Sorry for being late. 1 minute.
No, that's perfect. Thank you very much, Andrea. Thanks for making the nice link between the simulations and the observations and trying these nice images. All right, are there any questions? Maybe online? Yeah, Geneva, please go ahead.
Okay, thank you for the nice simulations. So you know the binaries is very popular in all stars, including AGB stars. If we put one of your model in a closed binary system, I believe the model will be maybe very different. Could you comment on this, the possible differences?
Yes, this is a good point. Of course, everything here has been shown as the star was alone. If you put a very close binary, I suspect that the interaction with the one could actually change the convective pattern we see here. And of course, this is something that has to be taken into account, in particular for what we're talking about, also for all kind of observation afterwards. So the convective pattern is expected to change. The mass transfer is expected to change, and also suspected that the distribution of the density between the two stars, and so the binary system itself, the inclination, how is actually seen by us from the observer, could be changed by the interaction between this large convective macro turbulence and the formation of a Roche lobe and mass transfer between the two stars. So this is, of course, something that has to be explored more deeply, I think. I agree on that. But it's something that is important for closed binary. So it's also this term close is important. So I don't know if you have a problem with connection.
Yeah. For closed binary case, is there a possible way to tell the difference of binary or from the irregular images you showed in your model of a single star?
Using interferometry, you mean, right?
Yeah. If we see the high resolution maps, it's not spherical, but can you tell it's a single star or binary?
Yeah, but you see that the star has been shown by Susanna from this thing. The star is not spherical, in particular for AGB stars. I mean, the station of the photosphere is already something to be taken into account. But I believe that the star is very close by. If there is like some close by companion, this anomaly should be even pointing towards the direction where the star should be. We have some something observables in the sky that we can actually, it's something difficult to disentangle. I mean, the convection is very high in terms of velocity, and the extension of the photosphere, this kind of star, is very large as well. And it's not spherical, again, it's not regular. So
thank you, mate. Yeah,
okay, thank you.
To go to the next speaker. Thank you, Andrea, for your talk again.